So first things first, it gives you the goals for today. I've actually collapsed both classes into one PowerPoint presentation. So rather than having to switch over from one to the other, I'll just continue. I mean, we'll have the break as usual, but rather than me having to stop and then go to another one, I just put everything together into one presentation. So going to understand the meaning of multiplying a vector by a scalar. I mentioned this yesterday, but we're going to go into a little bit more detail on it. I'm going to understand how collinearity of vectors is related to scalar multiplication of vectors. I'll do a demonstration of that. We'll understand unit vectors, vectors that have a distance of 1 or a magnitude of 1. I shouldn't say distance because magnitude is really the more general term for how big a vector is, and that's not always distance. We'll be able to apply the concept of scalar multiples to problems. Okay, so what does that look like? Well, let me go over some of these vector properties first. Given a vector A, multiplying that vector by a scalar, right, just a number like 10 or 15 or whatever, will result in another vector Ka, so K times A with the following properties. If it's more than 1, and now it's going to make perfect sense to you, I think. If the K is more than 1, if this scalar is more than 1, then the K times A is going to have the same direction, it's going to be stretched by a factor of k. So, for instance, if k was, let's say, 3, it would mean that the 3 times the vector would be a vector which is just 3 times as long as its original vector, but it continues moving in the same direction. All right, that's all that means. It's been stretched by a factor of k. It's 3 times as long. If the k is between 0 and 1, so now we're talking about if it was somewhere here between 0 and 1, then that k is still going to move the vector in the same direction, but now it's going to be compressed by a factor of k. So a number like, for instance, 0.25. If there was 0.25 of the vector still runs in the same direction, but it now has shrunk by it's now a quarter of its original length by multiplying by 0.25. If the k is somewhere between -1 and 0, then because it's now going to be a negative scalar, it means that the vector has now changed direction and is going in exactly the opposite direction. It was going east, it's now going west. It was going north, it's now going south. It was going southeast, it's now going northwest. So it's the exact opposite direction. It's kind of like the concept that we mentioned yesterday of the the word just escaped me now. When you take the vector which has the exact opposite, goes in the exact opposite direction. Can't remember the word right now, but it's the same kind of thing where the vector just simply reverses direction. That's all it is. All right. So it's been compressed and also it's going in the opposite direction. That's both things are happening at the same time. It's a shorter vector and goes in the opposite direction. All right. If the k is just simply less than -1, so now we're down here, then what is happening is that you're going to have a number like maybe -4. So the vector is now changed direction, and it also is 4 times as long. It's stretched by a factor of k. So all of that kind of makes perfect sense. It's just taking your vector and either lengthening it or shortening it, and sometimes changing its direction. That's really all it is. Okay? All right. And I think some of that is fairly, I think that's it's almost common sense. What's a unit vector? Unit vector is a vector whose magnitude is 1. So not all vectors have magnitude of 1, right? But sometimes you need to be talking in terms of a unit vector. So the easy way to make a unit vector become a unit, take any vector, make it into a unit vector, is by multiplying it by this scalar quantity right here, 1 over the length of whatever the vector is. So just for instance, I'll just give you a for instance. Let's say this is my vector, and this vector is 7 long, right? 7 units long. And we're going to call this vector t. Then it means that the unit vector, oh, and by the way, I should put an arrow on this to say that the vector is going in this direction. So if I wanted to get the unit vector for this, I would just simply take the vector t and multiply it by 1 over 7, which would mean that the length of the vector, 1 over 7 times 7, would now be equal to 1, right? So that's what that means. If the vector has a unit, has a length of 7 units, then all I need to do is to basically divide the vector by whatever the magnitude is. And another way to do that is to multiply by 1 over that number. And that's really all that is. So the scalar quantity is 1 over the magnitude of the vector. That becomes a scalar, and that makes the vector now have a magnitude of 1. So this would become the magnitude of the vector. These are meant to be the lines around the vector to make sure that it now is a unit vector. Okay? All right, so that is all that is. Just multiply by a scalar, which can take any vector and make it into a unit vector. Simple, simple stuff. So let me give you a little demonstration now of what I mean by these various scalars. So if I use this vector in the top right-hand corner as being my vector A, and you can see that the vector is running sort of up and to the right as you go, as you move along. And the vector, just so you know, and I'll show you right now, has a magnitude of 2 centimeters. I'm using a little ruler here to show you what that magnitude is. Okay, Alexander. Alexander, this seems to be a daily thing. You know, you got to try and make sure you can stick with us in the class. We do have a break in the class, so try and schedule the times that you need to go for that. Okay, but anyway, go ahead. All right, so let's come back to this. So this vector is approximately 2 units long, right? So what would 4a look like? Well, 4a would look like that. It's just simply a vector running in the same direction as the original a, but it's just 4 times as long. So if this one is 2 units long, then this one is going to be 8 units long, right? So just 4 times whatever the original vector was. A vector of 0.5, again, just like the a up here, is going to be running in the same direction, just half as long. So whereas this one was 2 units long, this one is 1 unit long, being a half of the original magnitude. This vector of minus 2a, notice that it does have a magnitude of 4, because remember, the original vector had a magnitude of 2 centimeters. But now this vector is 4, but notice that it's running in the opposite direction. It's going down instead of going up, right? So whereas the original vector is up and to the right, this one is going down and to the left. Okay? So that's all that is. That is all that is. Very simple stuff. Now, let's go back to some stuff that we did yesterday. V and W are vectors acting at 40 degrees. So meaning 40 degrees is between the two tails of the vectors, right? Where the two vectors are meeting each other is where the 40-degree angle is. So if two vectors are acting at 40 degrees with magnitudes of 3 and 4 respectively, find the magnitude and direction of V minus W. Okay, V minus W. So let me try to put this together on a diagram for you. Here is V and here is W. Those are the two vectors. We're going to sort of pretend that these, when we put them together, have a 40-degree angle between them. Now, V is running up and to the right. W is running strictly to the right. It's running in an easterly direction. So how do I subtract them? Well, here's my V vector, what I'm pointing to right now. My W vector, though, is going in the opposite direction over here, right? So that's where it's going. Whereas the W vector is pointing to the right, the minus W vector is pointing to the left. Same magnitude, but it's pointing to the left instead rather than to the right. Now, the original two vectors, let me just remind you, when I put those two vectors together, there was a 40-degree angle between them. So this is 40 degrees right here. So what we're trying to find now is the magnitude and direction of the V minus W. So I put them tail to tail, as you can see right here. The V is going up, the W is going to the left, right? Remember, not to the right, because the original W is going to the left. Sorry, it's not going to the right, because the original was going to the right. This one is going to the left. So I put them tail to tail. Then I create that parallelogram around them, right? So here's the other W on top here, right? Moving in the same direction as the W that's down here to complete the parallelogram. And here's the other V up here. So what's really happening is that I'm moving from here and I'm ending up here, right? If you just follow that track, I'm moving along W, then I'm moving along V, which means I started off right here and I ended up right there. And I'm moving in generally this direction. All right, so what I'm asking you for is the magnitude of that line. That's the line I'm asking you for. So how we do this, the way we did it yesterday, we're going to use not the Pythagoras, because this is not a right triangle. What this is a triangle that can be calculated using the cosine law. Remember the cosine law from yesterday. So we have two distances. One is 3, one is 4. So let's say this is 3 here, and this is 4 here. What we're trying to find is the length of that dotted line. So what do you think that would look like if we were putting this into the cosine law? Well, it would look something like this. 3 squared plus 4 squared minus 2 times 3 times 4, cosine of 40. Why 40? Because the angle, now remember, the angle between the original vectors was 40, right? But if we were, and I'm just going to remind you of something. If we were summing the vectors, if it was v plus w, it would be this longer vector here, right? But because we're subtracting, it's actually the shorter vector that goes the other way. All right. And so what angles do you think we should be using? Should be using 40 degrees or should be using 140? We're using 40 degrees because we're trying to find the difference. If we were trying to find the sum, we'd have used the supplemental angle, which would have been 140 degrees, like we did yesterday. But because we're doing the difference, we actually use the 40 degrees. So here we go. 3 squared plus 4 squared minus all that stuff is equal to 2.57. So that would be what this distance is. Now, before I reveal how it can be done, how can we find the magnitude? Now, sorry, not the magnitude, the direction. When you give the direction, you can give the direction relative to one of the existing vectors. So it could be, let me just erase something here to show you what I'm talking about. It could be that we're trying to find either this angle here or this angle here. So relative to one of the pre-existing vectors. All right. I would suggest that we try to find the angle on top. So remember how we did this yesterday. Does anybody remember what strategy we used yesterday to find that angle? Does anybody remember the angle, the strategy we used yesterday to find one of those angles? So in other words, I want to be able to say that the resulting vector is this number of degrees from V or this number of degrees from U, from W rather. You're seeing the sine law. Thank you, Adam. Thank you very much. So here's the sine law. I'm going to put the sine of this theta, right, over 4. Actually, we could use, and again, it depends on which one you want to measure it from. But the sine of theta over 4, right, is equal to the sine of 40, which is what this angle is, over the 2.57, the one that we just got right here. So here's my 40-degree angle right here, right? Remember, that's the one that we said was between the two things, over the length of this line, the length of this line right here that we just found to be 2.57, the sine of 0, which we're calling this angle right here, over 4, which is the length of the line on top here. And if you did all of that, did the math on all of that, Adam, you're absolutely right. The sine law is what works. It works out to be about 89 degrees. Now, I probably should have asked you to do that for yourself because some people were having some trouble with this yesterday. But I just went ahead and calculated this ahead of time. And it works out to be 89 degrees. And again, you have to say when you're giving the magnitude that it is a certain number of degrees from one of the existing vectors. So we have two vectors that we can reference, either the vector v or the vector w. I decided to go with the angle between vector v and the new vector v minus w. So you can say it is 89 degrees from v, is what we're choosing to say. All right? Okay, hopefully that calculation makes sense to everybody. So I'm going to continue from there. And if you look at the top of the page, you'll notice that it does make the point angle between two vectors is defined as the angle formed when the vectors are drawn tail to tail. So that's why these two vectors are in fact drawn tail to tail. So here's my v vector, here's my minus w vector, but the angle between the original vectors v and w is what we're saying is the 40 degrees, but the v minus w means that the other vector, the w vector, is running in the opposite direction. Okay? All right. For the same vectors in example 2, find a unit vector in the direction of v plus w. So the unit vector, remember, has a magnitude of 1. So the first thing we need to do is to find the magnitude of this vector that we're trying to find right now, the v plus w. All right, so we're adding the two vectors together. So what will be the difference in the calculation, folks? Are we going to start with the sine law or the cosine law? And what angle do we use when we're adding it together? I've kind of given that hint to you already. What are we going to use? Is it the cosine law or the sine law to find the magnitude of this vector? And also, should I use the 40 degrees? If I take you back to this one, it was 40 degrees between them. The magnitudes are the same 3 and 4, right? V is 3 and W is 4. So tell us how we're going to do this. All right, come on, folks. I need to throw this out to the room and ask you for some reaction here. How am I going to find because remember, if I'm trying to find the unit vector, I need to know the magnitude of the vector that's coming up. So can you help me out with that, please? Sine law, cosine law with an angle of 140. All right. Are you seeing what Adam just said? What do other people think about what Adam just said? Does that make sense? Should the cosine law be the answer? And is it 140 degrees, which is the supplemental angle that we should be using? I need to get some reaction from everybody else. Is Adam right? Or are people just not sure? Right? When you're adding them together, do we use a supplemental angle or do we use a 40 degrees? Okay, so Richard says he thinks so. All right, let me just call a few other names here because I'm not getting enough reaction from people. Brendan, what do you think? Do you think that Adam is right? I'm not sure. Taj, don't know, to be honest. Okay, you're guessing. Well, I'm not going to react. I'm not going to respond yet. I just want to know what other people think. I was just asking Brendan. Brendan, what do you think? Does that make sense based on what we've done so far? Or is there another strategy that we should be using? Brendan, where's Brendan? Seems like the best way to go. Yeah. Seems like a lot of people aren't so sure about this stuff. But yes, it is in fact going to be the cosine law. And yes, it is in fact going to be 140 degrees. Why? Because I'll show you why. If you're adding together the v vector, so consider this to be the v vector right here, and consider this to be the w vector right here. The angle in between them is the one that we're saying is 40 degrees. But if I'm trying to find the dotted line, and what I need is this angle over here, right? I need these two sides, and I need the angle in between them. And since this is 40 degrees right here, it means that the supplement of that is the one that's in the corner, which is across from the vector that we're trying to find the magnitude of. Okay? And that's why we're using the 40 degrees, sorry, the 140 degrees, and that's why we're using the cosine law, because we have the two angles, the two sides, and the angle in between them, and that's why the cosine law makes sense. So in this case, it's equal to 6.59. That will be the magnitude of the vector. Now, we want to find a unit vector in the direction of v plus w. So we now know what the magnitude of this vector is. To find a unit vector, we do this. We take 1 over, and this is where you can write it, 1 over 6.59, because this is trying to divide the v plus w, right? This resulting dotted line here, which is the v plus w line, we're trying to make that to be a unit length of 1. So we're going to in fact, what we're doing is dividing it by 6.59. Since the magnitude is 6.59, if I want to make it a magnitude of 1, I divide it by whatever that magnitude is, and that will give this a magnitude of 1. Okay, so the unit vector in the direction of v plus w is 1 over 6.59 times the sum of the v plus w. That's one way that you could actually write that. Okay, all right. Folks, you need to let me know when something isn't clear, because you know I'll stop and I'll go over it again. I'm quite happy to do that, but I can't do that unless people are giving me an indication that they're not so sure. Why do we need a unit vector? Good question, Adam. And as we do some more vector algebra, you'll see why unit vectors are important. I would change the magnitude. We are making the magnitude consistently 1. So anytime you hear that this is a unit vector, it means that the magnitude of that vector is in fact 1. And as I said, when we do some more vector algebra, the purpose of that will become more clear. So when you hear the term unit vector, anytime at all, always consider that magnitude to be 1. Okay? So we're only changing the magnitude now, Adam, by the way. We're not changing the direction of the vector. Right, the direction stays the same. All we're doing is shrinking it, or if it was a vector which was less than 1, enlarging it to make it have a magnitude of 1. Okay, so let's try this now. Let's try this. Let's see how well we do with this. I give you two vectors, x and y, and they're unit vectors. So there you go. The term has come up right away. So that means that each of them, when you start off, has a magnitude of 1. They have an angle of 30 degrees with each other, between them. What's the value of the magnitude of 2x plus y and the direction of 2x plus y? Give the magnitude to one decimal place and the direction relative to either vector x or vector y to the nearest degree. Okay, what does that tell you about the magnitudes of the vectors that you're working with? Since the original vectors were 1 unit long, all I'm really doing is making it twice as long. So it means it's going to have a magnitude of 2 units now. And the original vector y stays with a magnitude of 1. So in a sense, it makes sense for us to put a diagram that, oh, sorry, let me take that. Oh, geez, I'm going too fast here. Let's put this together carefully in a diagram, right? Let's say that this is vector x, and let's say that this is vector y. The angle between them is what we're calling 30 degrees. Now, x has been doubled, so I really should make this twice as long, like putting it all the way up there, right? So what would be the magnitude of the vector if it was multiplied by 2? Well, the original vector was a unit vector, so that would suggest that this vector can be regarded as being 2 units long. The vector down here, which is a unit vector, that didn't change, so that's going to be 1 unit long. Okay? So now we're trying to find the magnitude of the result of adding these two together. So let us go ahead and put in the other vectors. This is another, actually, let me erase this here. That's too long. Oh, sorry, didn't mean to do that. So this is 2 units long, and this one is about this long, so that's 1 unit long as well. Actually, you know what? This should be shorter. If I'm trying to be proportionate, then this one needs to be shorter, right? So let me try to change. Actually, you know what? I'm just going to erase the whole thing and start again. Let's try this again. So I'm doubling the length of this one. So this is going to be 2 units long. This one is going to be 1 unit long, so half the length. The angle between them is 30 degrees. And I'm trying to find the magnitude and direction of the resulting vector. So I'm going to go ahead and fill out the parallelogram. There and there. Then there's going to be a dotted line that goes between them. And this one is 1 long, this is 2 long. All right. So, all right, I really am going to expect some input from you. How do I find, let's call this line here x plus y, which is what it is. Vector x plus y. That's the diagonal line that goes in between those two. So walk me through, tell me, first of all, what we're going to use to find this. What angle are we going to use? And is it cosine law or sine law? I really need to get some reaction from people without me having to prompt you now. All right, so x and y, 2x plus y for the middle line. Yes, yes, absolutely. Yes, you're right, 2x plus y. Yes, you're quite right. Yes, thank you, Adam. Okay, so what are we going to use here, folks? All right, you know what? All right, it's time for me to start just calling out people in because we're just staring at the screen here. Fernando, let's get to you. All right, what do you think is the step that we need to take next to get this x plus 2x plus y? right? Can you walk me through what that might look? Fernando, let me just make sure you're there first. Are you there with us, Fernando? Okay, good. Can you give us an equation that would work? First of all, what are you going to use? You're going to use sine law or cosine law? Which one makes more sense to you? Cosine. Okay, good. So let's do this. Let me write the cosine law down for you. So a squared or is equal to actually. 1 second here. Sometimes I think the smartboard is actually easier to work with than the PowerPoint presentation. Okay, so a squared is equal to b squared plus c squared minus 2bc cosine of a. Okay, wait a second. How would you find the other angle here? Okay, Taj, that's actually a good question. When you're saying the other angle, I'm assuming you mean this angle right here. Is that the angle that we're talking about? Okay. Does anybody know how to answer that? That's a good question, Taj. Does anybody know how to? Taj, I'm going to come back. Fernand, I'm going to come back to you in a minute. 150. In other words, 180 minus 30. Absolutely. Because it's a parallelogram that we've created, Taj. It means that the adjacent angles, the angles that are right next to each other, are supplemental. So let's see what Fernando has. A squared is equal to 2 squared plus 1 squared minus 2 times absolutely cosine of 30. That's the only part I'm going to say is not quite right, but you're almost there. So this side that we're trying to find, which we'll call it a squared, is going to be equal to 2 squared plus 1 squared minus 2 times 2 times 1 cosine of, how do we correct the last part? Yeah, Tomaleo is right, cosine of 150. Because that would be this bigger angle here that is across from the side that we're trying to find. All right, Kushi, thank you very much. And Fernanda, thank you very much. Okay, so I kind of already gave that away. So I just put the answer in. Oh, sorry. It's 2.9 is that magnitude, all right? You should try that for yourself, right? And probably what I should have done is rather than just give away the answer, I should have asked one of you to get that done. But yeah, it is 2.9, approximately 2.9. You have to round a little bit to get that. So now they're asking for the direction relative to the nearest, so either X or Y. So we have to make a choice whether we're going to go with X or Y. And what I'm going to do is, let's see now. In fact, we'll do both. I will do both because, in fact, getting one of them is easy to get the other one. So let us say that we want to get this relative to the x, to the x. X is the longer line, which is this one up here, right? So just try to think of how we might be able to do that. All right, because I'm going to call on one of you in a second to see if you can help me out with that. So what we're trying to find here is this smaller angle right here, right? The one I just colored in. How do I get the size of that angle? Given that this is 2 right here, right? This distance right here is 2. This distance right here is 1. And we know that this line right here is what we call the 2.9. We just worked that out a while ago. How can we figure out this angle that I just shaded in a few minutes ago? That's what I want to ask of the class, right? And Javier, what do you think? How can I find that angle? Javier, your time. Check in for me, please. I want to find that angle up in top and help me to set that up. Good. Help me to set up that. You see where I just shaded in a few minutes ago, right? What would be a good way for me to find the size of that angle? The left angle. Yes, the one on the left, the one with the little dot inside of it. Correct. Give me some ideas as to how we might be able to find the size of that angle. Can you see where I put that in? Okay, good. I know my diagram isn't great. So folks, if you want to draw yourself a better diagram, be my guest. And I know that mine isn't that good. So let's hear from Javier on that one. Sine law. Okay, good, good. So set that up for me then now. What over what would be equal to what over what? Or would it just be 15? No, no, you can't do that. And that's a temptation I want you not to yield to, Javier. Don't think that because a diagonal goes through an intersection point, a vertex, that it necessarily splits it in half, because that is not always the case, right? If this was a square, perhaps, then yes, but it's not a square. And in fact, it isn't even a rectangle, right? It's a parallelogram. So let's try to set this up now to solve for one of those angles, or that angle that I just colored in right there. So I agree with you for sine law. By the way, I should let you know you can use a cosine law as well, right? You can use a cosine law because you have all three sides. So just pointing out, and we can try that. I can show you how to do this with the cosine law as well. But let's just get this with the sine law first, right? Can you set that up for me, please? Javier, can you help me to set this up? It's not 15. No, it's not just splitting it in half. So what over what is equal to what over what? I've kind of just been giving that to you all along, where I should be asking you to make sure that people remember how to use a sine law. And in fact, like I said, I'll show you the cosine law as well, approach to doing that, because you can use the cosine law to do the same thing because you have all three sides. Okay, so Javier, over to you. I'll remind you what the sine law says, by the way. Sine law says that either you put the side over the angle. We're trying to find an angle, so I'm going to use the sine. That's not sine, S-I-N, of A over the side A is equal to the sine of B over the side B is equal to the sine of C over the side C. Okay, but we only need two at a time. We don't need all three, right? We only use two at a time when we're doing this. So can you set, okay, so the sine of A, well, I guess you're calling A the one that we're trying to find. So let's put this down here. So the sine of A over, you're putting it over 1. Let's just see if that makes sense now. The angle opposite to it is 1. Okay. Is equal to the sine of 150 over 2. I actually agree with that. I actually agree with that. I'm going to show you why, for those people who aren't so sure. I'm pointing to the line that we're trying to find. Opposite to that line, okay, something is missing though. Something is missing. No. Something is missing. Yeah, that's wrong. That's not right. Sorry, I'll take that back. It's not over. No, sorry. It's not 150 over 2. Can somebody correct that, please? What's wrong with that? I don't know why I said it was that. That's not correct. Can somebody please correct that? Can anybody please correct that? So it's 150 over the 2.9. Yes, yes. So let me fix that. The side opposite to it is the 2.9. Okay. Vanessa, thank you very much. Adam, thank you very much. All right. Thank you, Javier. But can you understand why it is over 2.9 or rather than over 2? Does that make sense to you, Javier? Okay. So I'm going to ask somebody to calculate that. And then we're going to see if we can use the cosine law as well, because it's probably a good thing that I give you alternatives to doing stuff like this. So, Ella, are you there with us? Ella, are you there? Where's Ella? Ella, don't try to hide on me now. I think she's absent today. No, I just marked Ella here, didn't I? Let me just double check that. Ella was. No, Ella wasn't absent. Ella is here. So Ella, come on, you gotta get into it here. Where's Ella? Ella is not absent. Ella is supposed to be there. Ella, we're depending on you to participate along with everybody else. So please check in for me, Ella. Where are you, Ella? Might be getting a snack, yeah, but I didn't ask for any break. By the way, Alexander, are you back with us now? Alexander? Where's Alexander? Okay, good. Alexander, what do we ask you that? Go ahead and get your calculator. We're going to get back to Ella. Do the calculation for me, please. Sine of A over 1, well, good, luckily for you, it's just sine of A, is equal to sine of 150 over 2.9. Can you give us that angle, please, on your calculator? Ella, we're still putting a shout out for you. We need to hear from you, right? It's not break time yet. All right, so Alexander, give us that calculation, please. What's the size of the angle that's marked right here? So you're getting 9.9, he's saying. So 9.9. What units are we talking about again? What are we trying to calculate again, Alexander? What is it that we're trying to calculate here? Well, what units would make sense for what you just found out? 9.9. Remember what it is that we're calculating. It's degrees, absolutely. It is degrees. So that would mean that we could easily figure out the angle, and that's relative to the x vector, right? So by the way, everybody else get 9.9 because I haven't done the calculation yet. Right? Has everybody else got 9.9 for that? Okay. So that's relative to the x vector. What about relative to the y vector? What if I wanted to give the answer relative to the y vector? What's a quick way that we could actually figure that out? Adam, I've been in Radiant since yesterday. I got it. Yeah. Okay, I'm glad you figured out why things were going off the rails there. So just fix that. I'm sure you know how to change it over. All right, so what about the relative to the other vector? So we just got it relative to x. What is it relative to y? Can anybody tell me how we can figure out what it is relative to y? Right, it's 9.9 away from the original x. How far is it from y? Anybody? How far is it from y, folks? Still looking for Ella, by the way. Well, think about it. This whole angle, I'm going to point to it right now, is 30 degrees. Thank you, Alexander. This whole angle is 30 degrees. So wouldn't it make sense that if I found one part of that angle to be 9.9, that the other part of the angle is whatever is left over from that 30 degrees, which what Alexander just said is 20.1. So there though, let me erase all this stuff that's getting in the way here. It's 10 degrees from x and 20 degrees from y. And I'm rounding it to the nearest degree because that's what the question asked us to do. Okay? So I know that some of this stuff is new to a lot of you, or most of you. And I know that some of you may not be as good with the trig as you were when you first learned trig. But folks, this is the nature of the vector course. You're going to have to be very comfortable with trig. It's just the nature of vectors. All right, so there's your answers. 10 degrees from x, 20 degrees from y, and the magnitude of the vector is 2.9. Unit vector, when they gave us the question originally, is basically just saying that since it's 2 times that, it's now 2 units long, and this one, since it's a unit vector, is just 1 unit long. So when you're putting your diagram together, you can now have magnitudes along each of those original vectors. Okay, now let's put some of these vector skills to work, right? Let's see if we can do this. This might take us a couple of minutes to get done, but I want you to follow along with me here. This is a triangle ABC, right? And a median means it splits a side in two, is drawn from vertex A to the midpoint of BC. So this D splits this BC line exactly in half. It's right in the center between both of these. If AB is B, that's labeled on the diagram, and AC is C, that's also labeled on the diagram, prove that A to D, this line right here, is half of the B vector plus half of the C vector. So going from here to here is actually adding together half of B. If you took half of B and half of C, it would actually give you this vector. Now remember that the direction matters. So if we're talking about the B vector runs from A to B. What I should do is put a little arrow on here for you to be able to see that more clearly. Sorry. Let me go back. Give me a second to get back to the pen here. Okay, so let me put a little arrow on here. That we're going from A to B, and a little arrow here. That means that we're going from A to C, so that we don't confuse ourselves as to what direction we're talking about for B and what direction we're talking about for C. Somehow, we need to be able to prove, I'm going to go through this step by step, that this line going from A to D, so here's what we're trying to prove, that the line going from here to here is the sum of half of this vector and half of that vector. Somehow adding half of each of these two vectors takes you from A down to D. Okay, so here's a step-by-step procedure for that. First thing, let's accept, hopefully, that to get from B to C, right, to go from this starting point right here that I'm pointing to this ending point right here, I can take the trip by going in the opposite direction of B. So if you see me tracing out my line right here, you know what I'm noticing? That sometimes that because I'm using a white background and a white cursor for the mouse, sometimes hard to see the arrow. What I need to do is probably change the background to a darker color so the contrast will be easier for you to see. But anyway, if I go along this vector, which is minus to the B vector, then I go in this direction of the C vector. That will give me the BC line. So to get from B to C, rather than going straight across from B to C, I could go along this line, which is the B vector line, but in the opposite direction to B. So that's referred to as minus B. And then we're going to go along the C line, which would mean that I am going to end up at C eventually, which is what I want to do. I want to go from B to C. So I'm going along this line, then I'm going along that line. Okay? Hopefully that makes sense to everybody. Let me do a quick room check to make sure that what I just said was fine. Ella, still looking for you, right? You're supposed to be in the room, and we're going to have to figure out why you're not there. But let me go to, let's see, Christopher. Christopher, are you there with us? Christopher, where are you? Okay. Did that sentence statement make sense to you, what I just said? Hello, hello. Yeah, we're calling for you before, Ella. You got to stay with us. Okay, call several times. But Christopher, does that statement make sense to you? What I just said to you, does that make sense? That BC is equal to minus B plus C? How does that sound to you? Does that sound about right, or do I need to go over that again? I'm fine with doing it if you're not sure. Kind of. All right, let's do this then. Let me slow this down. All right. I want to get from here, and I want to end up over here. Okay, Christopher? That's where I want to start. That's where I want to end. I want to start here. I want to end here. So rather than going straight from B to C, can I not go along this line here that I'm pointing to? Can I not go along that line first and then follow this line going down the other way? Do you see what I'm saying there, Christopher? Can I not do that and still end up at C? Can I not start off at B, go up this line here, okay? But going up this line means going in the opposite direction to B, because B goes from A to B. That's what this thing at the top says, that AB is equal to B. But if I want to get to C, I can go along B in the opposite direction. Then I can go along C in the same direction as C, right? Because C goes from A to C. So to get from B to C, I can do a minus B plus C. So you're saying you get that now, Christopher. I just want to check in with you to make sure you got that. Right, that makes sense. Okay, perfect. So that's the first thing I want to start off by saying. Now remember, my goal here is to come up with something for AD, which we'll get to. Here's my second statement. BD, to get from B to D, can we agree that that will be half of the BC line, right? From here to C. If I want to get from B to C, I could go, sorry, from not B, from B to D, I can do a half of the BC line, right? Because remember that the D point is halfway between B and C. All right, let me do another room check on that to make sure everybody's okay with that. Kushi, how about you? Does that, Kushi, just check in for me first. Let me just hear from you first. All right, did that statement, the BD being half of BC, does that work for you? Does that statement make sense to you? It does. Okay, let me keep going then. Remember, I want to get from A to D, but I'm just trying to come up with some other relationships first. Can you say that again? I can, Tash. Thank you. Thank you for asking. So what I'm doing is I'm saying, first of all, did you get the first line that BC is minus B plus C? Okay. So BD now, to go from B to D, right? I can take a half of the BC line. Here's my BC line running from, hold on a second. Just 1 second. Oh, actually, I can use a laser pointer. Let me try that. Yeah. To go from, actually, this might be easier for you to see using a laser pointer. All right. So I want to get from B to D. Can you accept, sorry, can you explain again how we got the minus B plus C? I sure can. Let me just finish this first, Ariana. Thank you for asking. All right. So I wanted to get from B to D. And isn't that just simply half of the BC line? Here's my BC line right here, Taj, right? That's my B to C, from B to C. But isn't B to D just half of that? You see what I'm saying, Taj? I just want to make sure that that's clear to you. Taj, how about you? Does I do, but I just got confused. BC is equal to, oh, the first one. So it's the first one that people aren't sure of then. Okay, so let's go back to that then. Let's go back to that. I'm glad that people are at least chiming in now, because that's important to me that people are actually paying attention. To go from B to C now, and I think using a laser pointer is probably easier for you to see where I'm trying to get your attention to be focused. To get from B to C, instead of going straight across like this, can I use these two lines, the B line and the C line, these two vector lines, can I use that to get to C? Well, yeah, I can go along this line, then I can go along this line, and ultimately that takes me from B to C. If I told you, right, Taj and Alicia and everybody else, to go from B to C, then you could say, okay, Mr. Count, how about if I go to A first, then from A, I'll go to C. Would I not still get from B to C that way? Do you see what I'm saying for that? Right? Taj and Alicia and everybody else. Okay, but to go from B to C going this way, I have to go in a minus B direction first, because B runs from A to B, but I'm trying to go from B to A. So I'm going in a minus B. Here's what it says. Right up here it says that AB is A to B, going from A to B is B. So if I'm trying to go from B to A, that's a minus B, is what we're saying, right? And then we're going to go from A now to C. Well, that's just going along the actual direction of C. So that's just plus C. All right. So is everybody a little bit more clear on how I got BC to be minus B plus C? Okay. All right. I think more people are clear on how I can make BD half of BC. Am I right about that? Does that make sense? All right, let me ask a few other, okay, good. Because it says that D is in the middle. All right, perfect. So let me continue now. Let me see if I can press this and it will continue. No, I need to go back over here, apparently. All right, you know what? I can do this. Yeah. Nope, that doesn't work. Nope, that doesn't work either. All right, so I have to go back over here to get rid of the laser. So if that is the case, let's see if we can go back over here now. Then can I not also say that AD, which is the thing that we're actually trying to find, right? How do I get from A to D? Well, can I not go along B first, right? So I'm trying to get A to D now. So can I not go along B first and then take that BD that we just worked out a few minutes ago, right? The laser pointer actually is very useful. So let me use the laser pointer again. I want to get from A to D. I can see that. Is it the triangle law? No, it's not a triangle law. No. I'm just mapping a path here, Kushi. It's not a triangle law. Oh, actually, in a sense, it is. Now that I think about it, it's kind of like triangle law. Yeah, it is kind of like triangle law. So I want to get from A to D. So one way to do that, instead of going just straight across, is I can go down here, then I can go along here. So yes, I'm gonna take that back, Kushi, for AD. I'm gonna take that back. It is like the triangle law, right? So I want to go from here to here. So instead of going straight down, I'm going to take the B vector and then this BD line right here. Does that make sense to everybody? Let me get some reaction again from the room on that, right? Does that make sense? Okay. All right, so look at what I wrote down over here. That the AD line, the line that I'm eventually trying to prove, is equal to the B, going along the B vector, plus this BD line, which, by the way, we worked out to be equal to half of BC. So we're going to use all of that in just a minute, right? So I think I hopefully can see where this is going. So here's my AD by taking the B vector, right? And then this BD line, and that eventually takes from A to D. So where am I going with this? Let's see if you can see where I'm going with this then. That would mean that the AD line that we're talking about now is equal to B plus half of BC. What do I mean by that? Did we say that the BD, right? This BD here was half of BC. So I'm just making a substitution. AD is B plus BD. And what do we say BD was? Half of BC. Right? So it's really just a substitution at this point. Right? So I'm taking this BD that I have right here. Yeah, let me go back to the laser pointer. So I'm taking this BD right here and substituting it with what BD is, and I can write AD as being this thing right here. Okay? So I think hopefully you can see where I'm going next. I have something, so half of BC. We have a BC here already, right? We know what BC is. So can I not now make another substitution, right? Let's see now. Make another substitution. Still have to figure out, I think I might have to go back to the smartboard for some of this stuff because I'm finding it easier to negotiate the smartboard than this sometimes. Okay, so can I not therefore say that this, since this is half of BC and BC is this thing right here, so it's minus B, which is what half of this is, plus a half of C. So I'm really taking this thing here and halving it. So that'll be minus a half B plus a half of C. Oh, that might have been a big step. Does everybody see the step I just did? Look at the BC line here now. Okay, let's do this. Here's what BC is, right? BC is this thing right here. Put a half and multiply this by a half. So times it by a half. So that would be a half of the minus B and a half of the C. Can everybody see why that's okay for me to do that? Right? I'm taking out the BC. Thank you, Jordan. Right? And thank you. Okay, great. I'm taking out the BC and I'm putting in what the BC is, but taking a half of it, multiplying it by a half. Right? So that's what gives me this thing here. So now I can just do some simple math at this point, which is that AD is a half of, if I add together these like terms, B plus a half of B, sorry, B plus minus a half of B, I'm just going to get a half of B, and of course I have a half of C, which is what I was asked to prove in the first place. It's a bit circuitous. I'm going to leave this on the screen for a few minutes. It is part of the recording, but I know it takes a little while to sort of wrap your head around it, but it can be proven. All right, so we'll take our 5 minutes now. It's now 11:15. Sort of recover from that. All the people who need to go do their stuff, please try to reduce the amount of hall passes that we're taking because you leave, then you're going to miss out on stuff that we're doing. We come back at 11:20. All right, this one is going to be easier, I think. Right? I want you to look at when we add. It says each of the following vector expressions can be simplified and written as a single vector. Write the single vector corresponding to each expression and illustrate your answer with a sketch. We'll pass on the sketch part, but is there a way for us to come up with a single vector to represent the sum or difference of these vectors? One vector says I'm going from P to Q, then it says minus the RQ, then it says plus the RS. Where is that taking us? What is the sort of final, okay, what is the starting point and what's the ending point of putting all of this together is what we're after. So here's how I want you to think of this. Think of this minus RQ here as being the same thing as the QR vector. So all I've done is I've just reversed the direction of the RQ vector to give me the QR vector. because that's what a negative does. A negative changes it. It's just like what we said before. The negative as a scalar changes the direction of the original vector. So the RQ vector could be regarded as the QR vector now. So once I've done that, let me now try to line these vectors up. If I put the PQ vector first, followed by the QR vector, followed by the RS vector, and I added these things together, PQ plus QR plus RS in that order, that means what I did is I started at P, then I went to Q, then I went from Q to R, then I went from R to S. So what would be the final result of all of that? It's exactly what you think it is. It's a PS vector because I started at P and I ended up at S. Really that simple, right? So really, if you can just arrange them in a way that the ending of one vector represents the start of the other, then you can get what the final vector is by saying, well, if I start at P, went to Q, then from Q to R, then from R to S, really I've only gone from P to S. It's like putting them in order and realizing, can we go with that? I sure can, Ariana. So the first thing I did is I took the RQ vector and changed its order because there was a minus in front of it. So since there's a minus in front, consider this to be the same thing as the QR vector. So rather than going from R to Q, I'm really thinking that this will be the same thing as going from Q to R because of the minus in the front. Does that first part make sense, by the way, Ariana? Okay, so now I'm putting them in a certain order. I put the PQ first. I want to put it in a way, Ariana, where the ending point of one becomes the starting point of the other. So this goes from P to Q, this goes from Q to R, this goes from R to S. So since I stop at Q, this one takes it from Q to R, this one takes it from R to S. So really all I'm doing is going from P to S. That's all I'm saying. That's really all we're saying. This to this to this, and then finally P to S. Okay, you're welcome. Let's try the same thing here. At the PS vector, the RQ vector, I'm minusing the RS vector and I'm minusing the PQ vector. Okay, let's change the direction of both of these. So the minus RS vector is the SR vector and the minus PQ vector is the QP vector. All I'm doing is I'm taking each of these vectors and change them to being the vector which is going in the opposite direction. No, I'm going to try to arrange the vectors in such a way that the beginning of one, right? Sorry, the ending of one takes to the beginning of the other. Well, this order doesn't help me right now because I have PS, then RQ, then SR, then QP. So that doesn't work. So let's rearrange them. PS first, followed by the SR, so this one here, followed by the RQ, followed by the QP. So I've changed the order so that I go from one to the end, pick it up from there to the end, pick it up from there to the end, pick it up from there to the end. And now I can figure out what my starting and ending point is. And it turns out that starting and ending, or R, and it turns out that that is, I'm going from P to P, which is the same thing as a zero vector. So you really haven't moved, in other words, right? It's a vector, and I've talked about a zero vector before. It's a vector that has zero magnitude, right? And zero direction, right? So really you started at P, ended at P. So really you're dealing with the zero vector in that case. All right. I'd like you to try one for yourself now. Okay, I think I've given enough time for that. So let's start off with Kashaf. Kashaf, just check in for me first, please. Perfect. Can you give me the answer for the first one, please? Your answer for the first one. AE, you say. Next. Well done. Thank you very much. All right. And does anybody need us to go over that, or is everybody reasonably comfortable with AE as the answer? All right, if I get no response, then we're going to move on. Okay, nope. Nope, makes sense. Okay, good, good. All right, so that was Kashaf. All right, so Thomas, you're up next. Thomas, are you there? Can you go over it? Okay, yeah, we can. We can. Just give me a minute. Thomas, you have an answer for us? We can do that. We absolutely can do that for now. Just give me a minute, please. Thomas, let's get an answer from you first. Thomas, check in for me, please. Perfect. You're not sure? All right. So let's do this then, Thomas. Which of these? All right. Let me go back. Let me go back. Let me do the. Let me tell you what. We're gonna go with the first one that Kashaf did, and I'm gonna come back to Thomas after that. All right. All right. So let me grab my stylus here. And what I'm going to do first of all is I'm going to change this minus BA. And what do you think, Fernando, would minus BA be equal to? What is it the equivalent of for the Fernando? The AB. Okay. Uppercase is what we should use for this. So the AB. And the next one is the minus CB. What do you think that one would be a good one to use for that one, Fernando? So the BC. Okay. And finally, so I think you have the hang of this. And finally, the minus DC would be equal to what? CD. Okay. So now we have these four. We have the DE. We have these three others. We have to find a way that the ending of one is beginning of the other. In fact, it looks like if I just put the DE vector down here, right, then that's going to work. Because it looks like if you follow what I'm doing, let me use the pointer here, the laser pointer. Looks like if I go from A to B, then go from B to C, then go from C to D, then go from D to E, what I've actually done is gone from A to E. Fernanda, does that help you out? Putting it in that order. See, I put that first vector at the end because that's the most logical place for it to go. Let me know if that kind of makes sense to you. Where do you where do you get the E? Well, this says DE right here. The first one says DE. So I put the DE on the end here. Okay. So the vectors that you gave me, the AB, the BC, the CD, and the DE. So does that make sense now? Okay, you're welcome. All right. So I did that also for you. Okay, good. I did that also for Thomas. Thomas, I can give you another minute if that helps you out to see if you can figure out the next one from there. Or do you think you have the answer now? Do you need a minute? Is it PT? Well, what do other people think? Is he right? Is it PT? Does PT make sense to everybody else? Okay, let's see. Just give me a second here. Yeah, I'm definitely going back to the smartboard. It's a little bit tedious to go back and forth with this thing. Oh, sorry. Yeah, it is the PT vector. Okay. All right. So can we move along now to the stuff that we were supposed to be doing in the second class? Okay, everybody seems to have agreed with that. That's good, Thomas. Okay, thank you, Thomas. And Ariana, thanks for asking the question. And before that, thank you very much. Let's see, Kashaf for giving us the answer for the one before that. Okay, so vector properties. This is going to be short, I think, and sweet. I don't think we need to spend a lot of time on this. It's going to be, I think this one's going to be easier than the one that we just did. Going to understand the commutative, which we've mentioned before, associative and distributive properties for vectors, some of which we've actually used already. Going to extend these properties to scalar multiples of vectors. We're going to understand how the zero vector applies to vector addition. So let me go back here. Yeah, all right. So, oh, sorry, let me pause that. So I'm going to demonstrate the commutative property of vectors, which is something that I have mentioned before, right? I'm going to try to demonstrate that whether you add the vectors in one way or another way, that the result is still the same. So little animation that hopefully brings that point home. So here we go. So there's your first vector A. This is your vector B. And I'm using the triangle law this time. So A followed by B. And therefore, the resultant vector is that vector right there, the one that goes up and to the right. Now, I'm taking the B vector first this time. I'm taking the A vector, putting that next. Again, using the triangle law. And then the resultant vector is that same vector which goes up and to the right. So the order in which I put them together did not change the result, right? So there's a demonstration of that commutative property of vector addition, right? Somebody had asked that question before, and I'm just giving you a demonstration of the fact that it does work, all right? For addition, not for subtraction. And we certainly haven't talked about multiplication and division yet. We will talk about multiplication later on in the course. Okay, so there's a conclusion. The commutative property for addition of vectors is absolutely 100% proven. Now, how about what's called the associative property? Does it matter whether I take the A plus B first and then add on the C? Or what if I took the B plus C first? You know how brackets say you should do the brackets first and so on. So what if I added together the B plus C, then added the A afterwards? Does it make a difference? Well, let me show you how that one pans out. So I'm going to take the A plus B first and then add on the C. We're going to take the B plus C, then we're going to add on the A. And let's see if there's a difference in the result. So that's my A plus B. And that represents the sum of A plus B. Okay? So that dotted line is the sum of A plus B. I'm going to take that result, the A plus B. I'm going to add on the C. So remember, the dotted line represents the A plus B. And then we're adding on the C. And the result of that is that line right there. So that dotted line, which is going very steeply down, is the result of the A plus B first, followed by the C. Now let's put that aside for a bit, right? And let's get rid of all of this stuff here. Let's take the B plus the C first. So here's my B. Here's my C. I'm using the same triangle law again and adding those two together, which gives us that line. So this line now represents the B plus C line. I'm going to take that B plus C line and I'm going to add it to my A line. Right? So there's the A's being added on afterwards. The result of that is the same result, which is what we had before. Remember, that was the A plus B first, then the C. Now they all still line up together at the end because they're the same result. So that's what we call the associative law. Oh, sorry, the associative law for addition of vectors. That order does not matter. Okay? I don't know why the video is going again. Let's move on to the next one. The other vector property is what's referred to as the zero vector addition property. And it's kind of obvious. If you add the zero vector to any other vector, it doesn't change the vector. Okay? The zero vector does not have any impact on the vector. It's still going to be whatever the vector was in the first place. The associative law, if I have scalars, if I multiply a vector by a scalar, so n times a would be the scalar of n times a, then I multiply the result of that times m. I could have done that by multiplying the two scalars first and then multiplying that by the vector a. The result is the same. The distributive law, if I add two vectors together, if I add two scalars together and then multiply it by the vector a, it's the same as taking the m times the a and the n times the a and then adding those two together. So that vector property also holds true. It looks a lot like regular algebra, which it is. in a real sense, it is. Right? So the m plus n times a is the same thing as the m times the a, m meaning the scalar a times the vector a, and the n times the a, the scalar n times the vector a. Distributive property for addition, if I have two vectors added together and then I multiply that result by a scalar, it's the same as taking the scalar into that sum. So k times a plus k times b. Again, this is Algebra 101 from grade 9 being applied to vectors. Nothing new or exciting there. So let's use the appropriate vector properties to simplify. So really, folks, what I'm asking you to do is to go back to basic algebra from grade 9, right? We can use the distributive law for it. So these are vectors inside of the bracket. This is vector A. This is minus 2 times vector B. This is plus 3 times vector C. So I could just simply use the distributive law that we just talked about, put that 4 into this bracket, and then minus all of these vectors that are in the second bracket. In a sense, I'm distributing minus 1 into this bracket. So what do you think that looks like? It looks like this. It's 4a minus 8b. Let me get my laser pointer here. So it's 4 times a, so that's a 4a. 4 times minus 2b minus 8b. 4 times 3c, the 12c. Then I'm going to minus all of these. So each of these changes sign. So this was a positive 2a, it becomes a minus 2a, minus b, minus 5c. And of course, you probably could guess that we can put like terms together, right? So after that, what I'm going to do is, definitely going to have to go back to my smartboard. Give me a second here, folks. So I'm just going to put my like terms together. The 4a and the minus 2a gives me 2a. The minus 8b and the minus b gives me minus 9b. 12c minus 5c gives me 7c. As easy as that. Nothing more than that. Given that, here's example 2, that vector m is equal to these two other vectors with scalars, 2a plus 3b, and vector n is equal to these two other vectors with scalars, or with one scalar anyway. Use some of the properties of vectors to simplify 2m minus n. It is what you think. I'm going to take 2 times this, right? 2 times the first one, minus all of what's in here. And that's going to give us 4a plus 6b minus a plus 4b, which means that I can simplify to 3a plus 10b, right? And you said vectors were difficult. As you can see, you're applying basic algebraic principles to vectors.